Hello everyone, I'm Sonny Collado and today we got the final discussion. That is question 7. This one is thermodynamics. And I'm gonna give you the introduction to this topic. So, what are thermodynamics? Well, thermodynamics are the study of heat, energy, and work. The heat is gonna be how we heat something. The energy is gonna be the power released by chemical reaction. Well, the work is gonna be how we work it. So, to start, we're gonna tell the difference between the chemical reaction and the physical reaction in thermodynamics. In physical, no, in chemical, let's start with that one. We can say determine, no, find how much heat is released by by a combustion of a gallon of fuel oil, for example. Is one of the if one of the examples that we can get to use the thermodynamics in these cases. Then we got the physical uh, reaction. This one is gonna be, for example, um, find the energy that we get from boiling water or by boiling water. Uh, Pretty simple actually. So, thermodynamics is the study that will help us to know if a reaction will work or won't work, physical or chemical. So it's pretty important to know that the thermodynamics are going to help us to find out if it's gonna work or not. So um, to continue, we got in this topic we got two important things that can help us understand more of the surroundings and the systems. So we also that's the things that we got actually. The systems are gonna be the process under study, um, and the surroundings are gonna be the rest of the universe. Yeah, I know it's pretty wide, pretty big, but we can give an example to put it more easier. Let's say we got a box, and then we put that box inside another box. So the first box that is smaller than the other one, the small box, is gonna be the system, and the bigger box is gonna be the surroundings. All the things that are outside the system, inside the bigger box, is gonna be the surroundings. Okay, so with that clear, I can tell you the final thing for my presentation and get to the other ones. That the first law of thermodynamics. It says that the energy of the universe will be always constant. So, thank you so much, and let's go with my partners.
Hello, my name is Nathaniel Masinzapon, and I am doing spontaneous and non-spontaneous reactions for Chapter 7. Uh, most exothermic reactions are spontaneous. Exothermic meaning giving off heat, and most endothermic means that it absorbs heat and would feel cold if you touched it. Are non-spontaneous. Thermodynamics is used to predict reactions to occur spontaneously or non-spontaneously. And this is the factor that determines spontaneously is entropy. Now, according to the second law of thermodynamics, spontaneity uh, typically tends toward increasing randomness. Higher entropy means higher disorder, low entropy means less disorder, and there is no possibility for negative entropy. Now, as you can see here, we can determine which substances have greater entropy. Typically, gases have greater entropy, typically due to the looser molecules. Now, in terms of the entropy of a reaction, we can determine that by determining the products and the reactants, the entropy of both categories and subtracting them. Positive entropy reactions means an increase in disorder. Negative entropy of reactions means a decrease in disorder. As you can see here is the change into more spontaneous forms, solid melting to liquid, liquid turning to vapor, solute turning into solution. There is more disorder as the molecules become less structured. So, in conclusion, if exothermic and positive entropy, spontaneous. If endothermic and negative entropy, it's non-spontaneous. And most other factors usually depend on the change in heat or change in entropy. And here you can see a difference in, or like a experiment that involves entropy and how it becomes positive and negative.
My name is Valeria Hilsa. I'm going to talk about exothermic and endothermic reactions from chapter 7, which are two important types of chemical reactions studied in thermodynamics. So, thermodynamics is the study of energy, heat, and work, and it helps us to understand how energy changes during chemical reactions. An exothermic reaction is a reaction that releases heat energy into the surroundings. During this type of reaction, the energy released when the new chemical bonds are formed and is greater than the energy needed to break the original bonds. Because of this, there is a net release of energy. A common example is the combustion or burning of methane. Burning fuels, wood, or gasoline are the example of exothermic reaction because they give off the heat that we can feel. In an exothermic reaction, energy is considered a product of the reaction. On the other hand, an endothermic reaction absorbs heat energy from its surroundings. In these reactions, more energy is required to break the chemical bonds that is released when the new bonds form. Because of this, the reaction needs an outside source of energy to continue. A good example is the decomposition of ammonia shown in our chapter. Another everyday example is melting ice, which absorbs heat from the environment. In an endothermic reaction, energy is written on the reactant side because it's required from the reaction to happen. In conclusion, the main difference between these two reactions is simple. Exothermic reaction release heat, making the surroundings warmer, while endothermic reaction absorbs the heat, making the surroundings cooler. Understanding this reaction shall help us explain many everyday processes, from burning fuel to melting ice, and is one of the basic ideas in chemistry.
Hi, Dr. Sharma. This is Carlene doing my video review for Chapter 7. When it comes to what I found difficult in this chapter, this is another chapter that was pretty straightforward, and really glad that this is how we're ending the semester. I didn't find too much difficult in this chapter. Between going over like thermochemistry with the first, second, and third laws, all of it seemed pretty straightforward, and it made a lot of sense as I went over it privately. So I decided to do my chapter review on calorimetry, specifically regarding specific heat and heat capacity. So I wrote a couple notes. Okay, so specific heat of a substance is the amount of heat required to rise the temperature of 1 gram of the substance by 1 degree Celsius. The capacity heat is the amount of heat required to rise the temperature of an object by 1 degree Celsius. We can use the specific heat of a substance to determine the heat capacity of a specified quantity of the substance. So it's important to know, in this case, that heat capacity of 1 kilogram of water is going to be equivalent to 4.184 times 10 to the third power joules/Celsius. degrees Celsius. If we know the specific heat of amount of a substance, then the change in the substance temperature, in the sample's temperature, which is delta T, will tell us the amount of heat, which is Q, that has been absorbed or released in a particular process. So the equation when you're trying to define specific heat, it's going to be Q is equal to S, which is the specific heat, M, which is the mass, delta T. To find delta T, you need to know the final temperature and the initial temperature, and you'll be subtracting the initial from the final, and that will give you delta T. When it comes to heat capacity, it will be Q is equal to C delta T, where C is the heat capacity and delta T is the temperature change. The sign convention of Q is the same for that as enthalpy change. Q is positive for the enthermic process and negative for the exothermic process.
In Chapter 7, I learned about kinetics, which is the study of the rate or speed of chemical reactions. I learned that kinetics is different from thermodynamics. Thermodynamics it tells us if a reaction can happen spontaneously, but it doesn't tell us how fast the reaction will occur. Kinetics helps us to understand how quickly reactants are turned into products, and it can also give us clues about the reaction mechanism. I would say the main challenge with this topic I had was understanding the main difference between thermodynamics and kinetics, just because they seemed pretty similar at first. I also had to learn how it changes over time, like the disappearance of a reactant can be used to measure the reaction rate. To overcome all of these challenges, I reviewed my notes and I just compared the concepts, and this pretty much helped me to understand the topic a lot more.